Sena. In this lecture, we are going to discuss about power-aware multi-access with signaling, that is PAMAS protocol. This topic is present in the subject ad hoc and wireless sensor networks. Power-aware multi-access with signaling, that is PAMAS. The power-aware multi-access protocol with signaling is an energy-efficient media access control protocol for ad hoc networks. This protocol uses a separate signaling channel apart from the channel used for data transmission. The RTS-CTS messages are transmitted using this separate channel. Representation of power-aware multi-access with signaling. Here, in this diagram, the data is present in the node A. Node A transmits its information to node B. The A's transmission is overheard by node C. This is represented here. Using a separate signaling channel, PAMAS avoids the overhearing among neighboring nodes. Nodes shut themselves off when overhear transmissions. If a node has nothing to transmit and one of its neighbors being transmitting, if at least one neighbor of a node is transmitting or receiving, here is a representation. In this diagram, node A sends the information to node B. At that time, the node E should not transmit any data to node C. Likewise, node D should not transmit any packet to node F. That is, C and D should be power off. Here is a representation of the PAMAS protocol flow process. PAMAS protocol combines the busy tone solution and RTS-CTS handshake similar to the MACA protocol. MACA uses no final acknowledgment packet. A distinctive feature of PAMAS is that it uses two channels, namely a data channel and a control channel. All the signaling packets, that is RTS, request to send, CTS, clear to send, busy tones, are transmitted on the control channel, while the data channel is reserved for data packets. Consider an idle node X to which the new packet destined to a neighboring node Y arrives. First, X, that is the node X, sends an RTS packet on the control channel without doing any carrier sensing. This packet carries both X and Y's MAC address. If Y receives this packet, it answers with the CTS packet. If Y does not know of any ongoing transmission in its vicinity. Upon receiving the CTS, the node X starts to transmit the packet to node Y on the data channel. When node Y starts to receive the data, it sends out a busy tone packet on the control channel. If node X fails to receive a CTS packet within some time window, it enters the backoff mode, where a binary exponential backoff scheme is used. That is, the backoff time is uniformly chosen from a time interval that is doubled after each failure to receive a CTS. Now consider the nodes receiving node X RTS packet on the control channel. There is the intended receiver node Y and there are other nodes. Let Z be one of them. If node Z is currently receiving a packet, it reacts by sending a busy tone packet which overlaps with node Y's CTS at node X and effectively destroys the CTS. Therefore, node X cannot start transmission and node Z's packet reception is not disturbed. Since the busy tone packet is longer than the CTS, we can show that the CTS is really destroyed. Now, consider the intended receiver Y. If Y knows about an ongoing transmission in its vicinity, it suppresses its CTS, causing node X to back off. Node Y can obtain this knowledge by either sensing the data channel or by checking whether there was some noise on the control channel immediately after receiving the RTS. This noise can be an RTS or CTS of another node colliding at node Y. In the other case, node Y answers with the CTS packet and starts to send out a busy tone as soon as node X transmission has started. Furthermore, node Y sends out busy tone packets each time it receives some noise or a valid packet on the control channel to prevent its neighborhood from any activities. A node that receives an RTS packet while being in the backup state starts its packet reception procedure. That is, it checks the condition for sending a CTS. A node put its transceivers, that is control and data, into the sleep mode, and anytime a node knows that it cannot transmit or receive packets because some other node in its vicinity is already doing so. If a node X knows about the length of an ongoing transmission, for example, from overhearing the RTS or CTS packets or the header of the data packets on the data channel. However, often this length is unknown to X. For example, because these packets are corrupted or a foreign data transmission cycle starts when node X is just sleeping. Suppose that node X wakes up and finds the data channel busy. There are two cases to distinguish. Either node X has no own packet to send or node X wants to transmit. In the first case, node X desires to go back into sleep mode and to wake up exactly when the ongoing transmission ends to be able to receive an immediately following packet. Waking up at the earliest possible time has the advantages of avoiding unwanted delays. However, since node X may not have overheard the RTS, CTS or data packet header belonging to the ongoing transmission, it runs a probing protocol on the control channel to inquire the length of the ongoing packet. This probing protocol works similar to a binary search algorithm. PAMAS saves up to 60% of energy for low loads and a high node degree, and still between 20 and 30% are reached for low node degrees under a low load. In high load situations, between approximately 10 and approximately 40% of energy savings can be achieved with higher savings for higher node degrees.
Thank you very much for listening this lecture. For further updates, kindly subscribe this channel. If you like this video means kindly share this video to your friends. Thank you.